Hello and welcome to yet another lecture on basic electrical engineering, paper code ESEE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra, Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is construction and working of synchronous generators. Lesson objective. After end of this topic, students will able to understand the concept of construction and working of synchronous generators. So construction and working of synchronous generators. Contents. Today I am going to tell the introduction, construction of synchronous generator, working of synchronous generator, and applications of synchronous generator. So introduction, the electrical machine can be defined as a device that converts electrical energy into mechanical energy or mechanical energy into electrical energy. An electrical generator can be defined as an electrical machine that converts mechanical energy into electrical energy. An electrical generator typically consists of two parts. One is the stationary part called stator, and another is the rotating part called rotor. There are various types of electrical generators, such as direct current generators, alternating current generators, vehicular generators, human powered electrical generators, and so on. So, our today's topic is synchronous generator. The rotating and stationary parts of an electrical machine can be called as rotor and stator that I have already told. The rotor or stator of electrical machine act as a power producing component, and it is called an armature. The electromagnets or permanent magnets mounted on the stator or rotor are used to provide magnetic field of an electrical machine. The generator in which permanent magnet is used, the generator in which permanent magnet is used instead of coil to provide excitation field is termed as permanent magnet synchronous generator, or also simply it is known as synchronous generator. The generator in which permanent magnet is used instead of coil to provide excitation field is termed as permanent magnet synchronous generator, or simply called as synchronous generator. So our first portion is the construction of synchronous generator. A synchronous machine work, works as an alternator when the rotor is rotated by a prime mover. The same machine works as a synchronous motor when a three-phase AC supply is applied to the armature winding. The field being excited by DC supply in both cases. The construction of a synchronous generator depends upon the type of prime mover used to rotate the rotor. The types of prime movers are, the first one is the in thermal or nuclear power stations. Steam turbines are used to rotate at a high speed, that is of 300 rpm for a two-pole 50 Hz machine or 3000 rpm for a two-pole 50 Hz machine and 3600, that is 3 3600 rpm for a two-pole 60 Hz machine, 3000 rpm for a two-pole 50 Hz machine and 3600 rpm 3600 rpm for a two-pole 60 Hz machine. As at higher speeds, the efficiency of steam turbine is comparatively higher. For hydroelectric power stations, hydroelectric turbines of different types are used depending upon water head available in that station. In diesel station, lower rating alternators are used with diesel engines as prime mover at low speed. In captive power plants, high-speed gas turbines are employed. In captive power plants, high-speed gas turbines are employed as prime movers to rotate medium capacity alternators. So, this is the pictorial view of construction of synchronous generator. In general, synchronous generator consists of two parts. One is known as rotating part or rotor and another is the stationary part called stator. The rotor part consists of field poles and the stator parts consist of armature winding or armature conductors. So if I see this pictorial view, a three-phase supply is provided, phase A, phase B and phase C. This is the field winding which is excited by the DC voltage, that is the rotor field winding, and which is excited by the DC voltage, and this is called the stator or the armature winding. This is a two-pole machine, and the negative terminal for each phase is 180 degrees from the corresponding positive terminal. So this is the general pictorial view of a synchronous generator. The rotation of the field poles in the presence of armature conductors induce an alternating voltage which results in electric power generation. So this is the general construction of synchronous generator. So I have already told that the synchronous generator generally consists of two parts. One is the stator and one is the rotor. So the stator part is the stationary part. The various parts of the stator include frame, that is the pictorial view of stator, a stator frame that we have seen, stator core, the stator core that we have seen is the core of the stator windings and cooling arrangement. The armature slots are there, stator frame is there, stator core is there. This is the pictorial view of stator. frame may be cast iron for small size machines and welded steel type for large size machines. In order to reduce hysteresis and eddy current losses, the stator core is assembled with high-grade silicon content steel lamination. A three-phase winding is put on the stator or put in the slot skirt on the inner periphery of the stator as shown in the figure. The winding of each phase is distributed over several slots. When current flows in a distributed winding, it produces an essentially sinusoidal distribution of EMF. So another part is called the rotating part or the rotor. Rotor, there are two types of rotor depending on the construction, namely called the salient pole and the cylindrical rotor type. So this is a 6-pole salient pole rotor where we see the damper bars, steel spiders, shaft, rivet, pole face, pole body, and the field winding. Pole body, pole face, rivet, shaft, steel spider, damper bars. So first we will start with salient pole rotor. The salient means the projecting. Thus, a salient pole rotor consists of pole projection out from the surface of the rotor core. Since the rotor is subjected to changing magnetic fields, it is made of thin steel laminations to reduce eddy current losses. The salient pole rotor have concentrated windings on the poles. The salient pole rotor have concentrated windings on the pole. The damper bars are usually inserted in the pole faces. This is the pole face that is seen in the pictorial view, and the damper bars are usually inserted in the pole faces to damp out the rotor oscillation during the sudden change in load condition. The damper bars that is seen here, this is the pole face, and it is usually inserted in the pole faces to damp out the rotor oscillation during the sudden change in load condition. A salient pole synchronous machines has non-uniform air gap. The air gap is minimum under the pole centers and it is maximum in between two poles or in between the poles. The air gap is minimum under the pole centers and it is maximum in between the poles. The pole faces, the pole faces, the pole faces are shaped in that way that the radial air gap length increases from pole center to pole tips, so that the flux distribution in the air gap is sinusoidal in nature. This will help the machine to generate the sinusoidal EMF. So the individual field pole windings are connected is the field winding. The individual field pole windings are connected in series to give alternate north and south polarities. The end of the field windings are connected to a DC source that we have already told through the brushes on the slip rings. The slip rings are metal rings that is mounted on the shaft and insulated from it. They are used to carry current to or from the rotating part the machine via carbon brushes. Salient pole generator have a large number of poles and operate at lower speeds. A salient pole generator has comparatively a large diameter and short axial length. The large diameter accommodates a large number of poles. Salient pole generators driven by water turbines are called hydro alternators or hydro generators. So another classification of the rotor is cylindrical rotor. Another classification of the rotor is cylindrical rotor. Two pole and the four pole cylindrical rotor, that is the two pole, and there is a four pole cylindrical rotors that we have seen in this picture, in this figure. A cylindrical rotor machine is also called a non-salient pole rotor machines. It has its rotor so constructed that it forms a smooth cylinder. The construction is such that there are no physical poles to be seen as in salient pole construction. Cylinder, cylinder rotor are made from solid forgings of high grade nickel chrome molybdenum steel. In about two-thirds of the rotor periphery, slots are cut in regular intervals and parallel to the shaft. The DC field wing or the DC windings that called are accommodated in these slots. The windings of distributed types, the unslotted portion of the rotor forms pole faces. The windings are of distributed types. So, the smooth rotor of the machine makes less winding losses and the operation is less noisy because of uniform air gap. So, this is a two pole and four pole cylindrical rotor that we have already seen in this picture, in this figure. Cylindrical rotor machines are driven by steam or gas turbine. Cylindrical rotor synchronous generator are called turbo alternator or turbo generator. Such machines are always horizontal configuration during installation. The machines are built in a number of ratings from 10 MVA to 1500 MVA. So, the speed of field poles in synchronous is known as the speed of field poles is synchronous speed and it is given by that is known to us. Synchronous speed is 120 F by P, where indicates the frequency of the alternating current and where P indicates the number of poles, that is synchronous speed in S equal to 120 F by P, that is known to us. So the working principle of synchronous generator. Our next part is the working principle of synchronous generator. The principle of operation of synchronous generator is electromagnetic induction. If there exists a relative motion between the flux and the conductors, then an EMF is induced in the conductors that is known to us. If there is a relative motion between the flux and the conductors, then an EMF is induced in the conductors. To understand the synchronous generator working principle, let us consider two opposite magnetic poles, north and south poles. In between them, a rectangular coil, that is ABCD coil, is placed as shown in this figure. So in this figure, two opposite magnetic poles, that is north and south pole, and a rectangular coil, that is ABCD, is placed between the north and south pole. This is a rectangular conductor placed in between two opposite magnetic poles, that is shown in this figure. So, if the rectangular turn rotates in the clockwise direction, that is the direction of the rotation. If the rectangular turn rotates, this is the direction of the rotation, means the direction of the rotation is in the clockwise direction against the axis AB. This is the axis A and B. This is the axis shown by the dotted line. The axis is shown by the dotted line AB. Then, after completing 90 degree of the rotation, the conductor sides AB, that is the conductor side AB, come in front of the south pole, and the conductor side CD, that is come in front of the north pole, as it is seen in this figure. The AB, that is come in front of the south pole, and CD come in front of the north pole. The arrow that indicates the direction of the current and also the figure, that is the direction of rotation of conductor, that is perpendicular to magnetic field. Thus, now we can say that the conductor tangential motion is perpendicular to the magnetic flux. The tangential motion of the conductor, it is clearly seen in this figure. The tangential motion of conductor is perpendicular to the magnetic lines, that is coming from north to south pole. The magnetic lines that is coming from north to south pole, the tangential motion of the conductor is perpendicular to the magnetic flux that is coming from north to south pole after 90-degree rotation of the rectangular conductor in the clockwise direction against the axis A, B, this axis. So, the rate of flux cutting by the conductor is maximum, and induced current in the conductor, the direction of the induced current can be determined by the Fleming's right-hand rule. So we can say that the current will pass from A to B, and from C to D. Current will direction of the magnetic field, that is this one, the direction of the magnetic field, and from north to south, and current, and this is the direction of the rotation. So the direction of the current that will be given by the or determined by the Fleming right-hand rule. We will see that in our next slide, the Fleming's right-hand rule. So if I apply the conception of Fleming's right-hand rule, see that the direction of the current will be from A to B to C to D. If the conductor rotates in a clockwise direction of another 90 degree, then it will come to a vertical position. It will come to the vertical position as shown in the figure. So it will come to a vertical position, as shown in this figure after 90-degree clockwise rotation. So this is the Fleming right hand rule. It is given that Fleming right hand rule for generators shows the direction of induced current when a conductor is attached to a circuit moves in a magnetic field. It can be used to determine the direction of current in a generator winding. So, it can use to determine the direction of current in a generator's winding. So, the Fleming right hand rule said that the right hand is held with thumb, index finger, and index finger and middle finger mutually perpendicular to each other at right angles as shown in this diagram. Thumb, middle finger and index finger are perpendicular to each other at right angles. The thumb is pointed in the direction of motion of the conductor relative to the magnetic field. The thumb that is pointed in the direction of the motion of the conductor relative to the magnetic field. The first finger is pointed in the direction of magnetic field, that is north to south, is known as the direction of field. This is the direction of motion, this is the direction of field. Then the second finger represents the direction of induced or generated current. Second finger that is shown the direction of current, that is the direction of induced or generated current within the conductor from the terminal with lower electric potential to the terminal with higher electric potential as in a voltage source. This is the Fleming's right hand rule. This is known as Fleming right hand rule. So now the position of the conductor and magnetic flux lines are parallel to each other. Thus no flux is cutting and no current will be induced in the conductor, that we have already seen. Then while the conductor rotates from clockwise for another 90 degrees, the rectangular turn comes again into a horizontal position, such that the conductors AB and CD are under North Pole and South Pole respectively. By applying the right hand rule, current induced in the conductor AB from the point B to A and current induced in the conductor CD from point B to C. Again, the 90-degree clockwise rotation means the rectangular turn, that is from the horizontal position, that is the rectangular turn that is in the vertical positions previously, it is come into the horizontal position, and previously it is seen that the AB is under South Pole and CD is under North Pole, but now it is changing. The AB became under North Pole and CD becomes under South Pole, that we have told that AB and CD, that is AB becomes under North Pole and CD becomes under South Pole. So when we apply the conception of Fleming right hand rule, the current in the portion AB is point from B to A, while current induced in a conductor CD is from B to C. But it is in the previous discussion that we have seen that current in the AB is When AB is under south pole, the current direction is from A to B, and when CD is under north pole, the current direction is from C to D. But after the rotation, means after 90-degree rotation, it will come into this position that is called the vertical position, and again after 90-degree rotation, it will came into the horizontal position, and where AB and the CD now come under north pole and the south pole respectively. And now applying the Fleming-Rayton rules, in conductor AB, the current is flowing from B to A. By previous case, it was flowing from A to B. And in case of the conductor CD, the current is flowing from B to C, where in the previous case, it was from C to D. So there is a change of direction of current. So the direction of the current can be indicates that A, B, C, D, and the direction of the current for the previous horizontal position that I have already told in the rectangular term, that is A, B, C, D. So the previous position, the direction of the current is A, B, C, D. But here A, B, C, D. But here it will be A, D, C, B. So if the turn, previously it was A, B, C, D, and now it is A, D, C, B. Now if the turn is again rotate towards vertical position, then the induced current again reduced to zero, that we have already seen. Thus, for one complete revolution of rectangular turn, the current in the conductor reaches to maximum and reduces to zero. And then in the opposite direction, it reaches to maximum and again reaches to zero. This is already shown in our previous slides. Hence, one complete revolution of rectangular turn produces one full sine wave of current induced in the conductor, which can be termed as generation of alternating current by rotating a turn inside a magnetic field. So, this is the output from the synchronous generator. This is a pictorial view. If we consider a practical synchronous generator, the field magnet rotates between stationary armature conductors. The synchronous generator, rotor and shaft or turbine blades are mechanically coupled to each other and rotate at synchronous speed. Thus, the magnetic flux cutting produce an induced EMF which causes the current flow in armature conductors. For each winding, the current flows in one direction for the first half cycle and current flows in other direction for the second half cycle, that is already shown in our previous slides and already known to us, with a time lag of 120 degrees as they displace by 120 degrees. So the output power is shown in this figure, that they are 120 degree displays, 0 degree, 120 degree, 240 degree, 360 degree. So this is the first cycle. They are, again it is, the second one is from 120, third one is 240 and so on. So they are 120 degree time lag as they displace by 120 degree. So for the first cycle, the current that is first half of the cycle, the current that is flows in one direction, and for the second half of the cycle, the current that is flowing is in the opposite direction. This is the voltage output and it is clearly shown in this figure. For one cycle, for one complete cycle, for first half, voltage is in one direction, and for the second half, the voltage is in opposite direction. And for the three phase, they are 120-degree time lag, as they are displaced by 120-degree in space, or they are displaced by 120-degree. This is the output. There is a voltage versus time graph, or the output power of synchronous generator. So the application of synchronous generator is that there are three-phase synchronous generators have many advantages in generation, transmission, and distribution. The large synchronous generators using the nuclear, thermal, and hydro system for generating the voltages. The synchronous generator with 100 MVA power rating uses in generating station. The synchronous generators are primary source of the electrical power. For the heavy power generation, the stator of synchronous generator designed for voltage rating between 6.6 kilovolt to 33 kilovolt. So these are the application of synchronous generator. So today we will see that we have already shown, or today we have already learned the construction, working principle, and applications of synchronous generators. Thank you.